I'll now hand it over to Peter.
Okay, here we go. We'll start off with temperature. The topic really is global warming. So warming suggests temperature. And really, we need to be thinking partly about unprecedented temperature or unprecedented temperature rises. So we'll go through temperature from 30 years back to 540 million years in various steps. We'll have a look at the greenhouse effect, adding CO2 to the atmosphere, trapping outgoing long-wave radiation and causing a lot of concern. Then we'll have a look at temperature and CO2 to see whether temperature seems to be greatly affected by CO2. We'll have a look at the emission rates of CO2 by country, by what's going in and out of the sea, what's going in and out from the atmosphere, those sorts of things. And if we still have time, rainfall, snow and ice, and the cycles that are going on. We should probably stop and have a quick question or two at the end of each of the topics. Anyway, here we go. Hang on, I'm not as well set up as I thought. I'll keep talking for a bit while. I'm not talking from a PowerPoint presentation. I'm talking directly out of the database that has about 400 data sets that I've collected so far. I'm a bit of a hobbyist, I guess, a bit of an obsession, a small boy with an album for data sets and things. The world is an oyster. There's data sets everywhere. Here are the sort of things that I've collected data sets on: cyclone activity, heat content, ice areas, oxygen isotopes, snow extent, sunspot numbers, volcanic eruptions, but not all for tonight. Right, here's a temperature data set. It's a daily one. Now, this is a daily one for the world, and it's all over the place. This is not what you'd feel at any point in the world, because we're only seeing a change of a couple of degrees. If you were at a point in the world, you'd feel changes of 20 degrees a day. Obviously, it's infeasible to look at daily data for very much. There's just too much clutter. So we've got to get deeper in than looking at daily data. Well, here's 30 years of monthly data. That's somewhat clearer. We can see that the world average temperature each month goes up and down a degree or two, but that's not what people feel. That's what not plants. Plants don't feel the 1 degree up and down of the mean temperature. So we have to keep remembering we've got to use statistical techniques and other techniques to enable us to see the wood from the trees, to see what's happening in the longer terms and things, but that's the small variations we see in the long term are not what anything natural feels.
And just in that, Peter, 1998.
Well, there's a bit of a spike there. Yep. Yeah, okay. So what usually happens to get rid of the up and down seasonal variation, we usually go to seasonally adjusted data. So we look at what's the average up and down throughout the year, and we subtract that out. So what we've got here is the unusually hot months, even though we're not seeing the up and down. So is that sort of clear? You know, seasonally adjusted is important. It allows us to see the changes, but it minimises our impression of what's really happening. It allows us to see the wood, but we lose all of the trees.
So the data is satellite?
Yeah, so what we're looking at here is satellite data. Now, the reason satellite data appeals to me is that there are two sets of satellite data that are in somewhat competition, and they agree pretty well. They're different groups that run it, different satellites, I believe, and the satellites, each satellite system covers the whole world, the whole globe very regularly. And there's no need to collect data from lots of disparate people from different countries, from different organisations, and then go through elaborate statistical techniques to put data from 7,000 sites together in order to come up with some world temperature or trend. The one satellite system does it nicely and accurately. They do adjust their data from time to time as they discover a slightly better correction for something, but there's really, if you looked at their data 5 years ago, it looks very close to what you see now. So here's 30 years of satellite data after it's been seasonally adjusted, and it's global data. So they've averaged together the data from the satellite as it goes round and round. So what we see here is, here's 2000 onwards, gone up and down, not too much change. There's a big bump here, an El Nino. Back here, we see some rapid rises for 3 or 4 years. We might get excited, things are really heating up, but then they cooled. And then things are heating up again, and then they cooled. And this is fairly typical of every slide you look at, that stuff goes up, stuff goes down. If you looked at this, if you were trying to make predictions on the basis of the 30 years here, you could calculate a statistical trend of about 1 degree per century. So in 5 generations, we would experience a 1 degree change, whereas if we were looking at our hourly data, we'd get 20 degrees in 1 day, and 20 degrees between summer and winter, and probably 20 degrees between the tropics and the poles. So we're looking at highly massaged data when we get to this stage. The satellite only looks at a little bit at a time. It doesn't. It's not like looking at Jupiter or something like that, where we look at the albedo of the planet, in just a few pixels. The satellite has a reasonably small reception beam and can tell when it's over ocean, land, when it's in various latitude zones. So here are the latitude zones that the UAH satellite, University of Alabama at Huntsville. So if we look down through the trend per century over here, there's some really big ones here. So these guys are in trouble. 3 degrees a century. That's a lot more than most people have heard mentioned in the press. But over here, we see that's in the Northern Hemisphere polar areas. Well, the guys that live up there are probably quite happy to have a few centuries of 3 degrees a century. If we look down a bit, there's a bunch of negative here. It's getting colder. Well, they're in trouble, particularly it's the South Polar area. So if penguins get a vote, they'll probably want to put up lots of CO2 if that works. Australia, about the 1 degree per century. In fact, most of the positive trends, the upward trends, are all Northern Hemisphere. So to some extent, if this is a problem, it's more a Northern Hemisphere problem than the Southern Hemisphere. Down in the Southern Hemisphere here, we see 0.3 of a degree per century, 0.6 of a degree per century. But 35 years is an awfully short period to be making any assumptions or prediction in the future. It's a bit like if you had temperatures measured every 10 minutes and you started your recording at midnight and you stopped your recording at 10 in the morning and then tried to predict what it would be like 2 days later or 200 hours later, you'd have a totally erroneous thing. So let's go a little bit further back. We can't use satellites anymore. 200 years back, we can go with thermometers. In fact, it can go back about into the late 1700s. Here are the 4 main data sets that use thermometers. Now, they're all 4 of them draw much of their land data from one common set, the Global Historical Climate Network. That's administered by the National Ocean and Atmospheric Administration in the US. There's all sorts of data in there. Some go back to the late 1700s, some go back 20 years. Some have almost no missing data, some were only up for 20 years. On these 7,000 stations, I haven't got that loaded here at the moment, but we have the unadjusted data and the adjusted data. And so you can look at what's been done what's been done by the National Ocean and Atmospheric Administration to this Global Historical Climate Network before these 4 groups get their hands on it. Then they do their own process. They discard a lot of the weather stations, which is fair enough, because some of them look basically crap when you look at them, so it's not unreasonable to discard some. They all have different ways of putting them together, different ways of processing them. The 4 data sets generally agree. The one that has the highest trend, GISS, Goddard Institute of Space Science, that's about a degree per century, whereas some of the other ones are somewhat lower. I would tend myself, if I had to pick one, I would discard the Goddard Institute of Space Science, because the fellow who ran that for most of the time was an outspoken climate activist. So I would tend to be a little bit suspicious of anything that comes out of there. The other outlier down the bottom here, the NOAA's one itself, it's the outlier compared to the other two, and also Dr. Thomas Carl, who recently retired, got up to a few questionable practices to get a paper out in a hurry before the Paris Climate Conference. The experimental database on which the paper was printed was based apparently is no longer available. It never went through the quality assurance processes and those sorts of things. So that gets down to Hadcrat 4 from the Brits, the Climate Research Centre, and the Berkeley Earth one, which is a sort of independent US one. Hadcrat 1, I didn't find the data very easily accessible. There was some metadata, some of the metadata I couldn't find there, so I couldn't make as much use of that data as the Berkeley Earth one. So quite often I'll be referring to Berkeley Earth as we go back 200 years. But remember, it's one of the 3 or one of the 4, and they all fit together reasonably well. Again, we're looking at smoothed, seasonally adjusted data that's gone up and it's going up and down 0.2 of a degree much of the time. There are some trends up here. 1975 onwards, they've all sort of gone upwards. 1940 to 1975, not done much at all, and a bit of slow rise from 1880 to whatever. The Little Ice Age only finished just off the graph over here, so it's a great relief to everybody to start this upward trend that's paused somewhat. So going a bit further back, 1,000 years, we're out of thermometers now, so we're into tree ring territory, sediments in lakes, those sorts of things. So here are a few of the well-known ones that came out here and made the headlines. The 2 hockey sticks from Jones and Mann, about 1999. Here's the hockey stick handle, and here's the blade on the hockey stick. Now, they were preceded, 1965, Dr. Herbert Lamb was the head of the Climate Research Unit before it was taken over by Professor Phil Jones. And this was Professor Lamb's reconstruction, a fairly significant medieval warm period, going down into the Little Ice Age. I'm not too sure quite what caused this blip, and then recovery from the Little Ice Age and up into the present. If you remember the ClimateGate emails, some of the significant ones that were quoted were referred to the need to get rid of the medieval warm period. It looks much more alarming, this bit coming up here, if you don't have this medieval warm period in here. And the scientists of the time were quite successful. They got rid of the medieval warm period.
Now, hang on, before you leave there. Mann's papers, Mann's paper has been thoroughly debunked by statisticians in Canada and the United States. And the 2001 UN's report featured Mann's... The UN's 2001 report prominently featured Mann's graph, and that drove scary headlines around the world saying we've got a problem. Al Gore featured it prominently, and then after it was debunked by reputable statisticians, including one who worked and gave evidence to the American Congress, the UN just pulled that little graph out of prominence altogether. It's complete rubbish.
Well...
No, if you just tell me.
No, I would have agreed with you until I'd collected more data sets.
Okay.
Now, here's the same period, going back 1,000 years as before, and here are two prominent ice cores, the Lower Dome ice core and the Greenland ice core. Now, they both showed declining trends until their data runs out up here. GISP2 is not much variation, perhaps a little bit more than Mann and Jones. Lower Dome has a good deal, lots more variation, but the longish term trend is fairly flat for 1,000 years, at least measured at the poles. Now, how representative the poles are, I'm not too sure. You have to take what data you can get, but if you look under the light post where the light is for something you lost somewhere else, I'm not too sure. But anyway, here are two data sets which are useful and go back a lot further, but in the same period as the hockey sticks, they don't show they don't go right into the present area with the upticks, but things have been fairly flat, at least at the poles. Or the other thing is the sample periods, the sample intervals make a difference. The GISP2 here, the one that doesn't have much variation, it only samples every 9 years, whereas the Lower Dome was about every 4 years. So with infrequent sampling, you can see you're not going to catch the big peaks and big troughs and things like that. You're not going to get El Niños or anything really exciting. The longer the sample period, and in the big long ice cores, it gets up to 1,000 years. So they're not going to see any alarming 50-year trends on something that only samples every 1,000 years. Okay, going back to the year dot, I guess 2,000 years. So we've got ice cores, tree rings, sediments, those sorts of things. Some of them show medieval warm period. They're presumably the ones, you see most of that in Northern Europe, but there's some evidence of it in other parts of the world, certainly not an entirely global phenomena. There's a fair bit of variation. You can kid yourself that things were a bit warmer back here, and then we slide down into the Little Ice Age, and then in the mid to late 1800s, most of them start going up, except this pessimistic one here of Lower Dome where things stay down. Well, I guess the Antarctica decided it wouldn't join with the rest of us going upwards. So what I get from that is things were a good deal somewhat colder not too long ago than they were in the first millennium up here, and perhaps we're climbing up towards that at the moment. Leaping further back to 10,000 years, a lot of this is, there's some ice cores. GISP is an ice core. Rosenthal did most of his work in the oceans, so it's sediment layers in the oceans. And from that, it looks like it's the coldest it's been for 8,000 years. So if we're warming, not surprising. It's the coldest it's been for 6,000 or 7,000 years. So Marcotte, this one has a very hockey stick-like appearance, hardly any variation at all, apart from the big uptick at the end. But most of the others have a lot more variation. Well, cranking further back, 50,000 years, all we've got now is ice cores. Well, there are some sediment ones for later on, but I haven't picked those up. So here we are 50,000 years ago, and we're up about here. And we can thank our lucky stars we're up about here and not back there. So that's about all I can get out of that graph, really.
So it's 10 degrees warmer?
Oh, 15 degrees if you believe the GISP2 ice core. Certainly 8 degrees warmer than all the other ice cores. Now, the ice cores are in the poles, but then again, they seem to be related to the temperature of the world. So thank your lucky stars that we're in the interglacial up here and not down in the ends of the ice age. Well, Here we,
Excuse me, Peter.
yeah.
I just want to acknowledge Pauline Hanson, Senator Hanson, who's just arrived. And also, I forgot to acknowledge Senator Giorgio at the back. Can you stand up, Peter? Everyone knows you, Pauline.
So heading further back into really dangerous territory, we're now back 350,000 years. And here we're starting to see cycles. Every 100,000 years, we come out of an ice age and we stay up there a little bit and then down we go. So the previous interglacials, I guess the three ice cores got a little bit out of sync. I think they really mean that there was one interglacial on top of each other here, but the three ice cores aren't exactly calibrated. But basically, we spend a little bit of time out of the ice age, and then down we go. And the previous one, 120,000 years ago, a little bit up at the top where it's nice and pleasant. Everybody likes it, Queensland-like weather. Then down we go. And here we are at the end of the longest interglacial for 350,000 years. So if you're a betting man and going to predict things, sometime in the next 10, 20,000 years, we've got trouble, big trouble. Back to the area where only geologists are game to go, there's a couple of ones going right back 540 million years ago. So it's been much hotter in these sort of peaks. Going down, a few other geologists, well, Scotese, we've got two of his goes, and another isotope one that's a bit different. These ones of Scotese's latest, these are big events with asteroid impacts or something like that. So I guess as he finds out more of those, this graph will get a little bit bigger or a little bit spikier, but there aren't really very many data points. So things have been a lot hotter and a lot colder and a lot everything. So what do you get from the temperature stuff? Well, things go up, things go down. Depends on the time scale you look. I'm not too worried about my grandchildren from what I can see from the temperature records.
So nothing unusual.
Well, things have been going up and down. In the short trends, long trends, all the trends in the past have turned around, except the current ones that are still going. And I imagine they'll all turn around as well. Will they turn around soon or not? Well, it's just like the stock market. If you knew when it would turn around, you'd know when to buy and sell. But you can look at the data and make your bet. Well, going on to the greenhouse effect. Well, let's just summarise the greenhouse effect. We've got the sun. The photosphere of the sun, 6,000 degrees. It's really hot. Not frighteningly hot. You can get 6,000 degrees almost on the end of your TIG welder in the workshop. But it's bloody hot. You know, things at that temperature radiate light, heat, infrared, ultraviolet, and pours out of the sun. Down through a window in the atmosphere, fairly transparent. That's why we can see. This is the window that lets this short wave radiation through to the Earth. Hits the Earth, warms it up. Not that much. The Earth's only 25 degrees or 30 degrees. Stuff that's at 25 degrees or 30 degrees doesn't radiate in the short wave stuff like that comes in. We don't see any light coming off it. Well, you do off the bottom of your mouse, but not off the top. There's no heat, there's no ultraviolet, no whatever. What comes off the stuff at 25 to 30 degrees is long wave radiation. So off the surface comes outgoing long wave radiation that's got to find its way up through the atmosphere. Now, the carbon dioxide molecules are particularly sensitive to some of the outgoing long wave radiation at around a particular wavelength, and they absorb it very readily. So the outgoing long radiation gets absorbed by the CO2. It doesn't hold it for very long. It re-radiates it, but not in the same direction, randomly in any direction. So a lot of the outgoing long wave radiation would have gone straight out if there were no CO2, but with the CO2, some of it gets re-radiated back down again, where it could be absorbed by another CO2 molecule and re-radiated in all directions. So it certainly slows the outgoing long-wave radiation. So as we add more CO2 to the atmosphere, the greenhouse theory says we'll be stopping outgoing long-wave radiation from the top of the atmosphere. So that's what the theory says. The CO2 concentrations are going up. We'll come to those later, but I'm quite prepared to believe that. There's a lot of measurements of that. And luckily, there's a satellite that measures outgoing long-wave radiation at the top of the atmosphere. So here's the CO2 going up, and here's the two satellite data sets at the top of the atmosphere measuring the outgoing long-wave radiation at 100, or at the top of the atmosphere anyway, which should now be reduced because of the greenhouse effect. And what we find, it's increasing. So the outgoing long-wave radiation is increasing, not decreasing as predicted by the greenhouse effect. So both of the satellite trends clearly show that it's increasing. Well, it's all over, Malcolm. Where's the beer? You want to go on?
Yeah,
to me, unless someone can find something wrong with that, I don't know why we're continuing.
And that's a NOAA satellite.
Yeah, I think so. There might be a sceptic up the back who's probably thinking, well, what if the output of the sun was going up fairly rapidly? You could then get the case where this extra shortwave radiation was coming down and the greenhouse effect was working really hard but still couldn't hold back all this increased shortwave radiation. So that might account for the increasing long-wave radiation in spite of the greenhouse effect. Well, unfortunately, it's quite easy to measure the total solar irradiance, and it's not going up. Here's the 11-year solar cycle. It varies only a little, but it's basically going down. And if you believe the Russian solar physicists, the next few cycles are going to be a good deal smaller than what we've had so far. So at the moment, it seems to me that the greenhouse effect itself is not looking too good. What's usually said then after, in the next paragraph, wherever you read, is that this temperature increase caused by the greenhouse effect will cause more evaporation of water. And this water is also a greenhouse gas, so that'll cause further trouble. So we expect to see...
So can you repeat that? Because that's the guts of it. They say carbon dioxide is not, it's only 0.04% of the atmosphere. So it's the water vapour that's going to magnify it. So what Peter's saying here is, where's the magnification?
Well, where's the water vapour? The water vapour is supposed to go up as the temperature goes up because of the CO2. Well, here's the CO2 going up, and you might say in this area from 1995, perhaps the precipitable water in the atmosphere has gone up. But in this area here, the CO2 was going up and the precipitable water vapour was going rapidly down. So either they have to add another clause to their suggestion about water vapour and say that between here and here it goes down and between here and here it goes up. It doesn't seem to add up.
And just on that, you can also say that the water vapour and the carbon dioxide have no relationship overall. So the water vapour started here, ended at about the same level, and yet carbon dioxide increased a lot.
Yes, basically. It doesn't seem to fit at all. Here's a couple of technical ones. This is the spectrum at the top of the atmosphere, how bright the top of the atmosphere looks. This is the region where carbon dioxide traps stuff. The green graph is what happens when there's no carbon dioxide in the atmosphere at all. So the atmosphere is quite bright all the way through this region here. The outgoing long-wave radiation is quite bright. As we add carbon dioxide, when we get up to 400 parts per million where we are now, there's a big cooling off in the carbon dioxide region. But going to 1,000 makes very little difference at all, from 400 to 1,000. In fact, in this region here, it goes the other way. So I'm not quite too sure what to make of it, but it certainly shows that most of the greenhouse effect has already happened. And this is summarised in the next one, both these graphs have come from the ModTran 6. It's an atmospheric radiation simulator, and I'm a bit weary of simulators, but this one's being used all the time to design satellites, observation systems and whatever. So if it was wrong, a lot of engineers and people would know about it, and it's up to version 6. They're regularly improving it and whatever. So one of the things it can do is measure the flux leaving the top of the atmosphere. This is in watts per square metre. When we have bar radiators of 400 watts, so you know what a watt is. It's not much compared to 400 watts you can feel. A watt you can't. Per square metre, it's fairly big. Well, what this is showing is we start off with a flux of somewhere around over 300 watts per square metre. We put in 100 parts per million of CO2. We've dropped it a fair bit. We put another 100 parts per million, so we're up to 200 parts per million. We didn't get much for our money there. Going up to 300 parts per million, we've hardly got any bang for our CO2 buck there. 300 to 400, forget it. Up to 1,000, there's only about 2 watts per square metre to be had. If we manage to get up to 1,000 parts per million, this basically the ModTran 6 simulator is suggesting strongly that this greenhouse effect has maxed out. There's nothing more to be had from it. We can double our CO2 and not expect much change at all from the direct greenhouse effect. People will postulate that there's all sorts of amplifying factors positive feedback factors and things. We'll touch on that a little bit later.
Before you go there, so 400 parts per million is where we're at now. 400 parts per million is where we are now. 400 parts per million is how much in percent? 0.04%. It's 0.04%. Carbon dioxide is called a trace gas because there's bugger all of it. And so even at that small quantity, if you increase it, it'll have no effect.
Well, now let's have a look at temperature and CO2 together. If CO2 is a main driver of temperature, we should see them moving together. We should see CO2 going up, temperature going up, maybe a bit of a lag. If CO2 goes down, we should see temperature go down. If CO2 is the main driver of climate that we've got to control. So let's start off with, here's 30 years, the satellite data and the Mauna Loa CO2 data. Now this is monthly, seasonally adjusted data. We'll see the unadjusted data a little bit later. It's really interesting on CO2. But what we see here is a steady march of CO2. Temperature, well, from here to here, it doesn't look like there's much going up from there to there. There's a pile here. This big blip there was certainly not caused by a big blip in CO2. So whatever it is that causes El Niños is far, far more powerful than CO2. There are periods of 3 or 4 years where temperature lurched steadily downwards when CO2 was going steadily upwards. Still, this is only 30 years or so. It might be abnormal or just a fluke.
Before you go on, just a couple of questions from... Before you go on, just a few questions from Facebook. We've got quite a few questions, but just in relation to what you've got so far. Peter, Glenn Graham asks, has anyone proven climate sensitivity in relation to carbon dioxide?
Howard will talk about equilibrium climate sensitivity a little later.
Okay. Another question is, does the EMF from NextRad and similar increase temperatures?
I have no idea. I'd have to... I'm the data set guy. Okay. I'm not the interpretation of atmospheric physics theory or anything like that.
Okay, keep going then.
So I'll look up those terms and have a look around and see if I can find 100-year data sets for them, or better still, 1,000-year data sets.
That's a question from Ronald Hollard. So you can put an answer to that on your page, which we'll give a URL to later.
Yeah, you'll have to give me clear notes there, and
Yep.
I'll have to work out what those terms are and see whether anything's been measuring them.
Okay. You can't read my writing?
No, not at all. Here we are going back to the thermometer era. Well, this looks pretty promising. Here's the CO2 rise through there. Temperatures went like that, went up here. Well, it was a bit flat here, but there. So that you'd have to say there's a pretty good correlation there. So maybe they're onto something. At least in the sort of 200-year period, it does look possibly promising. Ah, crap. Here we are. We've just focused in on this bit here. Now, if you have a theory and a law, it's got to apply universally. You can't just pick and choose when to apply it. So here's 1935 to 1980. Here's the CO2 trend, and here's the temperature. It doesn't seem to me to be any relation at all. Here's the Lower Dome ice core, measured both temperature and CO2 from the one core of ice. The CO2 measurements, I think, are much further apart, 9 or 10 years, whereas the temperature measurements are much finer. So what we see here is CO2 was fairly flat and temperature wiggled around and fairly flat. CO2 started to rapidly rise and the temperature fell. So that makes me a little less convinced of the long-term applicability of the greenhouse effect, at least in Antarctica and at least for the last 2,000 years. Here's the interesting part of Lower Dome, that bit there, blown up. So we can see the temperature measurements, the CO2 measurements, CO2 going up, temperature not going up at all, really.
Can you just go back to the other...
That one, the full Lower Dome one? Or that's...
What's the bottom of the arrows? 270?
That's part per million of CO2. So for quite a long time, CO2 stayed below 280. This rise above 280 is, at face value, at least a bit unusual. You have to, in order to suggest that it had occurred in the past, you have to bring in arguments like, well, the sampling interval is quite long, so there could well have been 50-year or 100-year trends or 500-year trends if you're only sampling every 1,000 years. So when we get to this one, things are, well, the CO2 is only sampled every 1,000 years, whereas the temperature varied from every 20 years recently back to 600 years, sort of further back. So this is the Vostok ice core in Antarctica, going back over 400,000 years, and it certainly looks like there's temperature and CO2 are strongly related. When they shoot up, they both shoot up together. When it comes down, it looks like temperature quite clearly leads. I mean, the temperature goes down as you're dropping into an ice age somewhat faster than the CO2 does. Now, I spent a while looking at the peaks and troughs, trying to convince myself what leads what. If you do a scatter plot of these and then fiddle with offsetting one with respect to the other to get the best correlation in the scatter plot, you can convince yourself that temperature leads CO2 by 500 years. But that's a bit chunky because the CO2 is only being measured every 1,000 years. Still, there's some statistical evidence that the temperature rise precedes CO2, and wiser people than me might hang their hat on that, but it seems a little flimsy, really, that we really don't have high resolution data to say terribly much. I mean, if you're only sampling it every 1,000 years, a great deal of interesting stuff occurred in the 1,000 years before present, which we don't see at all, only one data point as we go back.
By the way, to people on Facebook, keep the questions coming. They're good. We've got lots of questions, but I've only written a few down here, probably 8, on the actual data, and Peter will get to those as he goes on further. Trevor May asks, I think he's pointing this one at me, how's the Great Barrier Reef travelling, Dick Brain? So there you go. Thanks, Trevor.
We might be able to help you there.
With which part?
With the barrier reef.
Oh, right.
Yeah, the other bit.
Keep going in sequence, and you'll get to the barrier reef.
Well, the only thing I've got on the barrier reef is ocean acidity. If they're worried that it's going to dissolve or something, well, I can reassure them a little bit later.
Great, okay.
Here's the geologist at work again, going back 540 million years. Who knows? There's too much change. It's too long ago. We really can't tell what's going on there. So that was temperature and CO2. To me, the 100-year cycle, the 100,000-year cycle was fairly convincing. Either CO2 drives temperature or temperature drives CO2. Probably CO2 might possibly drive temperature on the 100,000-year cycle, or something else has changed. One thing that's advanced is the Milankovitch cycles, which I had to cut the number of slides down, but basically the precession of the Earth's pole goes around like that at 20,000 years or something. The Earth's orbit is not entirely circular. Sometimes it's more oblique, more eccentric than circular, and the Earth's inclination, the obliquity of the orbits changes over the 100,000 years timescale. If you add all that up, you can make a guess at what the intensity of the solar radiation on the northern hemisphere is over the 100,000 year timescale, and it fits in reasonably well, and a lot of people think that's at least a partial explanation of the ice ages.
So before going on, let's summarise. Is anything unprecedented happening with temperatures?
Oh, I couldn't see much.
Certainly nothing unprecedented. And there's no ongoing rise at the moment either, and it's more cyclical than anything else. Yeah,
I've got a whole bunch of slides to examine the pause, whether it is or it isn't. Looking at the satellite data sets over the pause period in the northern hemisphere, the southern hemisphere, the poles. You can look at that at various levels in the atmosphere. The temperature data sets, even GISS data set. So the chief scientist was waving around a GISS plot and looking at the little bit at the top. Well, I can show him what all the other 4 data sets show over that period, what the one his showed, and you can make your own opinion on whether it's up or down. It wiggles a bit. There's 2 big El Niños. I'm not too sure how you can have a statistical technique that makes adequate allowance for 2 big El Niños in the period.
So to summarise then, there's nothing unusual going on with temperature, certainly nothing unprecedented, and then there's nothing happening between carbon dioxide and temperature over a consistent period.
Well, certainly is at the 100,000 year period.
Nothing in the longer term or the immediate term, and certainly the long wave radiation leaving has increased rather than decreased.
Yes, so I'm not too sure how that works.
They're killers. The 2 fundamental things are just smashed right there.
Well, they certainly seem to start to stack up a bit. I mean, you need some cross-examination. This is just a pile of crap put together by a nerd. If there are other data sets that I can't find, we need to see.
But you're using the data sets used by the people who claim there's unusual warming.
Yes, in a lot in cases, yes.
Yeah. You're going beyond them.
Yes, just try to look further back, split the data sets in the way that was available but not offered, things like that.
So you've used the data sets that the people who are pushing climate alarm are using, and there's nothing unprecedented, there's no ongoing temperature rise, and there's no greenhouse effect.
Well, we didn't talk in great detail about the CO2 above 280 parts per million. From some points of view, looking at some data, you don't see much of that. But when you look at the sampling intervals of the data, you probably wouldn't if there were peaks and troughs on a faster timescale. If it's being lumped together in 50-year periods or 100-year periods, you wouldn't get the spikes and things. So I wouldn't bet my house on it, but it doesn't look too obvious.
So we shouldn't bet the country on it?
No, I wouldn't bet the country on it.
Okay.
Well, now we're still talking about CO2, but we're not talking about concentrations in the atmosphere. What we're talking about now is gigatons of CO2 going into the atmosphere or coming out of the atmosphere. So the first slide...
Hang on. Coming out of the atmosphere?
Oh, yeah, it comes out.
What do you mean?
It can come out at a huge rate. I'll show you later some cases where enormous quantities of CO2 come out of the atmosphere. Happens every year.
Okay.
So what we see here, these are some interesting countries and their CO2 emissions since 1960. Well, there's this guy here, it's the Chinese. They discovered capitalist industry or something here and they've gone berserk. I mean, that's just rocketing up. The next one is the Americans. Well, they discovered gas, cheap gas. So they've replaced some coal plants by gas. So their CO2 is falling, not by shutting down their industries or anything, but by burning gas. The Russians here, well, they were going up pretty steadily, but they had a bit of trouble with the Berlin Wall. And so it looks like getting rid of communism can bring down your CO2 emissions. So maybe we could try getting rid of socialism. It might bring down CO2 emissions if that's what we wanted to do.
That's telling as an aside, because in the late 1980s and early 1990s, the IMF and the World Bank bashed Russia.
Yes,
and caused a lot of economic damage.
Well, it's certainly reflected in CO2. This data stops about, 2012 or something like that. And we can see India just starting to ramp up as they discover, everybody wants electricity in all of the villages.
So they wanted comfort and longer lives and...
just a light and a refrigerator.
Just a light and a fridge, okay.
I mean, it's a big step forward.
So where's Australia?
Australia's here somewhere, the light green. We're down here. So here we are. This is a quick one on CO2 concentrations again. We can see the steady rise that's quoted.
Since when?
Oh, since 1960, sort of 2 parts per million per year, steady rise here, and maybe up to 3 parts per million up here. But what interests me is these rises here. From there to there, it's rising much faster than from there to there. So that's in one part of the year. The other part of the year, it plummets. So there's huge flows of CO2 into the atmosphere and out of the atmosphere, far, far more than the human flows.
And before you go, the human production of carbon dioxide in any one year is roughly consistent the whole year.
Yes.
So we're not causing that up and down.
No.
So that means when it goes down, nature is driving it down.
And that's completely obvious because the Mauna Loa station is run by the Scripps Institute. They have a line of stations from the South Pole to way up Alert Point and Point Barrow in Alaska and the Northwest Territories and Canada and whatever, way up in the polar regions. And it's those polar regions that have the huge changes of CO2 concentrations. They say CO2 is a well-mixed gas, but the South Pole and the North Pole have somewhat similar concentrations, but the South Pole has no seasonal change at all, whereas the North Polar ones have enormous seasonal changes. So here we are looking at gigatons per year. So this is the sum of all human emissions. This is an estimate. We don't have an emissions monitor thing anywhere. I mean, but economists measure things like this, and this is an estimate of all the human CO2 emissions from burning fossil fuels, from making cement and those sort of things. There's a couple of things I don't quite understand, why there would be a big peak here and a bit of a trough here, but nevertheless, the human CO2 emissions have gone up like that. Now, here's the zero axis, and this line across here is Australia's CO2 emissions. I mean, it's so indistinguishable from zero when looking at the world scale that it seems to me that the diagnostic manual for psychological and psychiatric diseases, DMS-5, well, when they have DMS-6, it's going to have a new psychological disease that says belief in reducing this at the cost of only $10 million a year or something is going to make any difference to that. To me, this graph is another complete stopper. Why on earth? The green line, this is what, if we take, this is what's happened to atmospheric concentrations. You can only change atmospheric concentrations by pouring CO2 into the atmosphere or out of the atmosphere. So this is what has had to have happened to the atmosphere in order to get the concentration changes. So these are all positive because the concentration's going up, but there's a fair variation in the rate at which it's gone up. Fluctuations that are not visible in these sorts of graphs. You're actually differentiating that graph in order to get this one. Now, the dark blue line here, this is an highly recognised committee of oceanographers and whatever have got together and looked at all the factors in the ocean that would be sinking CO2 into the ocean, and this is what they reckon is going into the oceans, about 10 gigatons per year at present. Now, the light blue one here that's all over the place, they call the land sink. This was the ocean sink, the dark blue one. But the land sink is just these other three added and subtracted together, and what's not accounted for, they call the land sink. To me, that raises some suspicions, because it's suggested here that this land sink, or whatever it is, can actually emit 1 gigaton per year into the atmosphere. And yet only a few years later, 5 years later, it's sinking 15 gigatons per year. Now, this might be increased tree growth or something, or it might be rotting vegetation, or it might be plankton in the oceans. I don't know what it is, but I'm sure there hasn't been, we would have noticed if the plants had been changing their behaviour so much. So to me, this raises a question of, until this is known, how can you predict anything?
Yeah, just sorry to interrupt. We're going to be running out of time if we don't sort of move.
We don't speed
along.
up a bit.
Yeah, either pretty quickly or...
Yeah, okay. Well, to me, that's a really big unknown. And if those processes, whatever they are, if they're temperature sensitive, well, it gets even more complicated and more unknown. There's the same graph going back to 1880. Things only really started after the war. Don't mention the war. Then they started to go up and down. Here's what's happening in the Northern Hemisphere. The blue one is CO2. The red one is CO2 concentrations. There's huge changes, dropping rapidly and then going right up like this. And this is the necessary change in gigatons per year to cause that. Now, I haven't taken into account whether it's spreading from La Jolla into other latitude zones and things, but these numbers are gigantic compared to the human emissions. And here's
so the variation in carbon dioxide in the Northern Hemisphere, is huge compared to what we produce.
Throughout the year, yep. There are huge flows in and out of the atmosphere, way strong, bigger than what the humans do. In fact, here's a plot of those wild variations against the human ones. Well, rapidly through rainfall. Here's rainfall back to 1900. I didn't show CO2 because you know that the CO2 has been steadily rising, and I don't see much change in rainfall since 1900. There's been a few more significantly wet years in the last 50 years than there was in the earlier 50 years. But with temperature going up, the rainfall doesn't seem to have done much. Bill probably mentioned the effect of rainfall on the measurement of temperature.
Can you go back? Just quickly on there, the Bureau of Meteorology, when it releases reports, if it says we're facing a drought and that'll scare us, then the Bureau of Meteorology tends to restrict the length of the data period that it discloses. So that it looks like it's falling in rainfall. But it's not. You can see there's no trend there over the last 116 years.
You can convince yourself that some of the time when the temperature goes up, the rainfall's lower. Or when the rainfall's lower and the ground's not so moist, it gets hotter. You see that there, you see that here, you see that there and there. But then there's other periods when it doesn't seem to be so prominent.
I'm going to have to cut in. We've probably only got till 9 o'clock and then staff are going to leave. So we're going to have got 25 minutes for everybody.
The snow extent follows temperature pretty well, as you'd expect. Sea ice in the northern hemisphere doesn't follow it quite so well. There seems to be some underlying downward trend in sea ice in the northern hemisphere that can't be explained by temperature. Southern hemisphere, it follows somewhat better. Here's the ocean acidity one. Well,
Are you watching Trevor May?
This was part of a topic I'm starting to get together on climate oscillations. Well, here is the ocean acidity measured at Arlington Reef off Cairns. It actually goes back to 1800. And what we see is steady fluctuations up and down, a couple of 0.2 apart. No upward trend with CO2 at all. You could say from those graphs that there's no acidification of the oceans going on at all. He is getting into some more fashionable, cunning plots on looking at oscillations. Well, here endeth the lesson.
Thanks very much, Peter. We're going to have to move along because otherwise we won't get through everybody. I'd like to introduce to you Bill Johnston. And Bill's going to be looking at the Bureau of Meteorology data and be able to show us some of the quality of it and the inconsistencies of it. So thanks very much, Bill. Over to you.
Thank you.